This week, I propose a foray into the world of mathematics. The subjects, probabilities, geometry, and the chaos theory. Games of chance have always been popular and sometimes ruinous. Fortunately, there's the theory of probabilities that may be able to save you from bankruptcy.
Many events in our lives are due to chance. Events we are unable to predict, we ascribe to chance. For instance, a couple who wants a child cannot predict whether it will be a boy or a girl. While we have no control over chance, we are at least able to calculate the likelihood of these events happening. Mathematicians have formulated rules that allow us to have an idea of the likelihood of certain events occurring. To understand these rules, let's use the example of games of chance. To calculate your chances of winning at one of these games, you have to identify all the events that could occur. For instance, in tossing a coin, there are two possible events. The coin can fall heads or tails. Both these possible outcomes have equal chances of occurring. So when we bet tails, we have one chance in two of winning. However, the more possible outcomes there are, the less likely the chances of one of them occurring. There is one chance in 6 of throwing a 3 at dice, since there are 6 possible outcomes which have equal chances of occurring. However, there are more complex situations. For example, what are the chances of drawing a heart face card from a deck of 52 cards? To solve this puzzle, we have to refer to a law called law of total probability. We know the player has one chance in 52 to draw, let's say, the King of Hearts. However, since there are 3 heart face cards in the deck, the chances of drawing one of them corresponds to the sum of the probabilities of drawing each of these cards. That is a 3 to 52 chance. The chances of winning at the roulette table several times in a row can be calculated by another law, the law of compound probability. Let's suppose a player bets on number 5. Since the roulette wheel has 37 numbers, 0 to 36, every spin of the wheel offers 37 possible events. The probability of the marble stopping on the 5 is therefore 1 in 37. Now each spin of the wheel is independent, which means that the first spin has no effect whatsoever on the second spin. So there are just as many chances of the 5 coming out on the second spin. However, the odds of the roulette wheel stopping twice in a row on number 5 are 1,369 to 1. This amounts to the multiplication of the odds of each spin, namely 1 in 37 on the first spin by 1 in 37 on the second spin. If another player first bet on number 5, then on number 12 at the second spin, he has the same chances of winning twice in a row as the first player, since each spin of the wheel is independent of the subsequent ones. The chances of winning a lottery that consists of choosing a combination of 6 numbers out of 49 are also calculated based on the law of compound probability. In this case, however, each time a ball is drawn, it alters the conditions of the subsequent draws. Suppose the gambler bets on the numbers 31, 32, 33, 34, 35, and 36. Since there are 49 possible outcomes, the probability of ball number 31 coming out first is 1 in 49. On the other hand, the second ball will be selected among the 48 remaining balls, since the first ball is no longer in the game. The probability of the 32 ball coming out will then be 1 in 48, and so on. In all, the probability of the chosen combination being drawn corresponds to the multiplication of the probabilities of drawing each of the balls. It comes down to one chance in over 10 billion. Fortunately, to win the lottery, the balls do not have to emerge in that particular order. In fact, according to another theory called the combinatorial theory, the 6 numbers selected can appear in 720 different orders. This means that the total probability of any combinations of numbers from 31 to 36 is therefore 720 times greater, namely 1 in almost 14 million. Here again, the probability is very low. Indeed, a particularly determined gambler who buys a ticket for every one of the 104 annual draws in this lottery would, on average, only win the grand prize at the end of 134,460 years. It's worth noting that the odds are the same whether you choose 6 numbers in a row or a combination of assorted numbers. Each of the 14 million combinations have exactly the same chances of being drawn, since the balls do not know what their number is. In closing, here's a little test. What are the odds of a couple with 5 sons and 1 daughter having a 6th son? Answer: 2 to 1.
Mathematics has many other applications than games of chance. For example, the need to measure expanses of land gave rise to geometry. The first surveyors noted that there were elementary mathematical relations between the angles, lengths, and surfaces of an area. While their techniques have vastly changed, the basic principles remain the same.
Geometry is one of the oldest branches of mathematics. Created by the need to measure spaces and to establish plans, Euclidean geometry, named after Euclid, the Greek mathematician who invented it, describes the various dimensions of the space in which we live. According to Euclidean geometry, the point is an element without dimension. The line possesses a single dimension, which corresponds to its length. The plane, whose surface is calculated based on its length and width, covers 2 dimensions. Finally, any body which occupies a given volume, such as a sphere or a cube, has 3 dimensions: length, width, and height. Euclidean geometry provides the means to measure distances, surfaces, quantities. Surveying, for example, is based on certain of its basic concepts. One such concept is the Pythagorean theorem, which applies to all right triangles. The square being the multiplication of a number by itself, the Pythagorean theorem states that the square of the length of the hypotenuse, that is, the square of the longest side of the triangle, is equal to the sum of the squares of the lengths of the 2 other sides. It follows that if we know the length of 2 sides of a triangle, we can figure out the length of the 3rd side. The concept of the angle is another basic concept of Euclidean geometry. Formed by 2 lines or 2 surfaces diverging from a common point, the angle is mainly used to describe a rotation. A complete rotation represents 360 degrees. If it only spans 90 degrees, it is a right angle. An angle is said to be acute when it measures less than 90 degrees, and obtuse when its value falls between 90 and 180 degrees. Today's land surveying devices make these measures automatically, but the procedures used are still based on the concepts of geometry. The land surveyor first determines 3 points in the environment and a reference line. He needs to know the distance of the elements to be measured in relation to that reference line. And such measurements cannot always be made directly. He will use the right angle to solve the problem. The operator sets the instrument up on one of the points of a triangle. If the surveyor wants to know the distance separating a given point from the reference line, the operator sights that point where a prism has been installed. During the sighting, the instrument sends infrared rays toward the prism. When they strike the prism, the rays are immediately reflected back to the instrument. The time it takes for the rays to go to the prism and back determines the distance between the telescope and the target. That distance corresponds to the hypotenuse, that is the longest side of the triangle. Then the operator swivels the telescope until he can sight the second target, situated at the end of the reference line. The instrument then records in degrees the rotation effected. That rotation represents the angle formed by the two rights, which join the two targets. There exist fundamental ratios between the lengths of the sides of a right triangle and the dimension of its angles. Each angle possesses a value called sine. That value is obtained by dividing the length of the side opposite to that angle by the length of the hypotenuse. By multiplying the sine of the angle by the hypotenuse, we can deduce the length of the opposite side. The land surveyor will thus know the distance between the sighted point and his reference line. Another concept of Euclidean geometry is that of the ratios between the various dimensions of an object, among them the surface volume ratio. That value is obtained by dividing the surface of an object by its volume. It changes as you increase the size of the object, since volume increases faster than surface. So for a small sphere with a diameter of 2 centimeters, the surface is about 12 centimeters squared, volume 4 centimeters cubed. The surface volume ratio is therefore 3:1. Conversely, if you quadruple the sphere's diameter, its surface will be 200 centimeters squared, its volume 268 centimeters cubed. The surface volume ratio then becomes 3:4. That is 4 times smaller than for the sphere with the 2 centimeter diameter. This concept has many applications, for example, in animal ecology. For instance, within a same species, the animals that inhabit cold regions are usually larger than their counterparts in warmer climes. Indeed, the larger animals present, proportionally, a smaller surface in relation to their volume. Since heat loss occurs at the surface of its body, this reduces energy loss. While formulated over 22 centuries ago, Euclidean geometry continues to have numerous applications in our lives today. For example, the shape of food cans was determined so as to minimize the surface volume ratio while allowing for optimum packing. This choice saves on the materials used to make the cans and increases their contents. The ancient Greeks probably had no idea that the applications of geometry would be so imperishable.
Once slaves to the abacus, modern mathematicians have greatly benefited from the advent of the computer. Thanks to this new tool, a new theory was developed. That theory, coined the chaos theory, attempts to describe the complex phenomena of nature.
The turbulence of rapids, the jumble of road traffic, an irregularity in heart rate, all these phenomena seem chaotic to us. Moreover, we have no way of accurately predicting their future state. And yet, in recent years, mathematicians have been studying these phenomena and trying to describe them with mathematical equations. They observe that in spite of their apparently anarchic behavior, chaotic phenomena are not necessarily governed solely by chance. They obey a hidden order. All chaotic events share a fundamental property, and that is a sensitivity to initial conditions. This property implies that two almost identical initial situations may evolve altogether differently. For example, observe the movements of two dead leaves on the surface of a waterway. As long as the water is calm, we can predict the movements of the two leaves, which follow very similar paths. However, when the current becomes faster and more turbulent, the leaves go off in different and unpredictable directions. Knowing what the weather will be like 3 days ahead of time is no less difficult. It was precisely when he was trying to figure out why we are unable to predict long-term weather patterns that the mathematician Edward Lorenz discovered the characteristics of chaos. He noticed that tiny variations in meteorological parameters, such as temperature, barometric pressure, and wind speed, can generate enormous differences in weather patterns. For example, while certain temperature, pressure, and wind conditions indicate fair and sunny weather ahead, a change in only the last decimal place in the numerical values of these conditions may bring us a storm instead. This phenomenon has been called the butterfly effect. A butterfly flapping its wings in China can, months later, trigger a thunderstorm in the West Indies. The atmosphere is therefore a system that is sensitive to the slightest fluctuations. According to chaos theory, the weather cannot be predicted accurately long in advance, because to do so we would have to know all the atmospheric data with infinite accuracy, which of course is impossible. But chaotic systems, whether raging torrents or atmospheric systems, obey more than mere chance. A certain order lurks within them. The existence of order within chaos becomes apparent, for example, when we illustrate the evolution of the atmospheric system graphically. After feeding into a computer the data related to the temperature, pressure, and wind speeds of a series of successive instants in the system, a strange butterfly-shaped figure appears. Even if each of the curves that make up this figure describes an uneven and unpredictable path, they all remain within the boundaries of the figure. For this reason, the figure has been called a strange attractor. But the shape of the strange attractor differs from one system to the next. For example, the graphic representation of the fluctuations of blood cell populations brings out an entirely different-looking strange attractor. A composite drawing of a chaotic system, the strange attractor, only reveals the main dynamics underlying a chaotic system. The fact that a snowstorm will never occur in a desert, for example. Here, chaos theory only has one good thing going for it, and that is to explain why it's so hard to make predictions. Indeed, even if we were to cover the surface of the Earth with atmospheric data sensors and use the world's most powerful computers, we still would not be able to predict what the weather will be like 3 weeks from now. The applications of chaos theory extend to such diverse disciplines as physics, medicine, and the environment. Some scientists use theory to better understand irregularities in the rate of heartbeat. To do this, they perform lab tests on samples of embryonic chick hearts. Similar to a complete heart, this aggregate of heart cells beats spontaneously. Periodically, the researchers stimulate the cells. By varying the frequency and intensity of the stimulations, they manage to alter the spontaneous beating of the fibers and make it chaotic. It is hoped that such experiments will help identify the mechanisms which cause this kind of heart rate disorder. In the future, they may well lead to the development of more accurate tools for early diagnosis and better therapeutic procedures than those currently available.
The chaos theory has many scientists dreaming. Some ambitious stockbrokers are even hoping it will help them predict market trends. This proves that while their heads may be in the clouds, some mathematicians do have their feet firmly planted on the ground.